let me start by thanking the organizers for inviting to this interesting workshop. So as I also think that the discussion of similar looking but different in physical context problems that we have here coming from different two communities, is certain to pay some dividends in short future, because there are some striking parallels that I find in this in the talks that I heard yesterday. So I am here to describe one particular aspect, which is, I think, very well familiar to all of you. So I would like to focus on particular magnetic anisotropy, Dzielaszynski-Maria interaction, and show how it strongly affects the physics and actually turns it into novel, turns into mechanism of reaching a new interesting states of quantum spins. And so, but before I start that, so I would like to show that the knowledge of Dzielaszynski-Maria interaction propagates into the community. So last night, as I was putting these slides together, I found that there is a band called Chirality, okay? And the name is not random, so they say chirality is just a cool word we learned from Breaking Bad. Okay, so, okay. I do have to do my homework to understand what Breaking Bad is, but I can, okay, understand that I'll describe that chirality is more than a cool word. So it's the plan is to, so I'll very briefly describe Dzielaszynski-Maria interaction, and then show that interesting, so there are materials still in interior definition in old condensed matter, which is done by material synthesized by chemists. So where there is a new interesting regime of interactions where we have chains with strong exchange interaction, and Dzielaszynski-Maria interaction is next interaction in order of magnitude, and then interchain interactions are yet much weaker. And in this new regime, or relatively new in the sense of experimental realization, very interesting behaviors are possible. And I'll show you a very simple-minded theory based on built on low energy excitations of spin half chain, where one can make a definite experimental predictions for the interplay of Dzielaszynski-Maria and magnetic field, and then one takes into account interchain interactions to show, I'll show that it leads to a new magnetically ordered state, which is very unusual from the point of view of standard quantum magnetism excitations. And but overall, my main idea is to convince you, if there is anyone need to be convincing, that Dzielaszynski-Maria can be much more than unknown material imperfection. It's not something which spoils an interesting model, it's something which makes it even more interesting and allows for us to study excitations which we couldn't study before. Okay, so so Dzielaszynski-Maria comes from the two names, and so D and M, and so the D and M are here, the papers from 57, 58, and 60, and so Dzielaszynski has proposed the asymmetric exchange interaction based on symmetry grounds, and then Maria shortly after, and probably independently, worked out the rules for this interaction. And so it comes, as we know, from spin orbital interaction. Provided the crystal symmetry allows for it on a given bond, introduces the symmetry of, if I think of Heisenberg systems, where originally its interaction is dot S dot spin dot another spin on neighboring side from SU2. So this term reduces symmetry to rotations about the d-axis. It results in an easy plane anisotropy when spins semi-classically would like to lie in a plane perpendicular to the d vector. And typically, we know it promotes magnetic order, and so it reduces the symmetry. As a result, it stabilizes a particular incommensurate, say, spiral phase, where momentum wave vector of which is favored by the d interaction. And this is all known. So also I saw the following yesterday's talk by Stefan Blugel here. So this is, of course, very well known in atoms community, where, for example, in this work it was shown that in this particular physical system of atoms, the DM interaction, which is most likely induced by some kind of RKKY exchange of spins via the conducting host, so favors particular chirality of out of two degenerate chiral states, a particular one selected by this DM interaction. Okay, but so my talk is focused on a material where geometry is slightly more involved and in an interesting, but in a simple and an interesting way. So this is material synthesized in Andrei Zholodyev's lab in ETH. It's a spin half insulator. Spins are coming from copper. And it's highly one-dimensional. And so that is parameterized in the following way, so that exchange interaction is estimated, and I'll later show in which way, to be of the order of 20 kelvins, and interchain interactions is at best 0.3 Kelvin. It's an estimate, it's not a measurement. It's an upper bound kind of thing. Okay? But what is most interesting is that so exchange interaction between copper spins comes via actually two bromine atoms, okay? And they are arranged in a way as shown here, so that from the super exchange pass is buckled, right? And so this by symmetry allows for Dzelashinsky-Maria interaction, and on neighboring chains, vector d points oppositely. So there is a unique crystal direction along which vector d can be pointing, and if on chain number 1 the d points along this plus z direction, on chain number 2 it points in minus z direction. On chain number 3 it will be plus z again. So it's staggered between chains, but within given chain it's uniform. It's the same d pointing, say, along plus z on every bond of that particular chain. Okay? And so these are two critical, crucially important properties which make for interesting story. And then, so experiments which I'll explain and substantiate with a simple theoretical description then allow us to extract this the magnitude of Dzelashinsky-Maria interaction, which is at least order of magnitude greater than interchain exchange, J prime. And so we exactly realize this sequence of scales in the problem, which makes for an interesting physics. And so what experimentalists did, they performed in ESR electron spin resonance experiments, and I'll go in slightly more details in a couple of slides, on this material. So ESR measures essentially energy absorption of a magnetic system in applied magnetic field. You apply magnetic field and you pump microwaves and you measure the absorption. And so in case of individual spin or weakly interacting spins, when we apply magnetic field, we Zeeman split them, and then the allowed transition would be the single Zeeman frequency. So it turns out that if you have strongly interacting system, but which is SU2 symmetric, so spins interacting only by symmetric exchange, then this remains true no matter how strongly spins interact with each other. In ESR experiment in such a ideal system, they only will give you a single response at a single frequency, which is the Zeeman frequency. Okay? In this experiment, so which results of which are summarized in these two plots, depending on how external magnetic field is applied with respect to crystal lattice, crystal axis. So one either have a response at a single frequency. So for a given magnetic field, there is single frequency at which absorption happens, or two frequencies. And these two frequencies, so if we have magnetic field, say, in AB plane, rotating magnetic field in plane from A to B, one goes from the direction when you it's along A axis, and then it's a single response. And then as you rotate H from A towards B, you observe two splitted resonances. Okay? And so similarly, you can apply magnetic field in AC plane and splitting, in which case no splitting is observed. It's a single frequency. Okay? So this is a kind of a puzzle for the, from the experimental point of view. So all measurements are done at temperature for the 1 Kelvin, right? So that it's well above any magnetically ordered state. So we have essentially decoupled spin chains. Okay? And so as I already said, ESR measures energy absorption. And importantly, it's a zero momentum probe. So applied external field is uniform, and microwave wavelengths of microwave radiation is usually much bigger than system size, sample size. And so it's Q equals 0 probe. And with respect to static applied magnetic field H, energy absorption is given by the correlation function of transverse components S minus, S plus, or XX and YY. With respect, magnetic field is along Z. Okay? And as I already mentioned, if interaction is pure exchange, then there should be single delta function-like response. And in avoiding for a moment question of line shape, here we have, depending on the direction of magnetic field, either single frequency or two frequencies. Okay? And so, so to kind of build up an understanding, so let's go slowly and ask what do we expect for magnetic electron spin resonance to show us if we think of ideal spin chain first. So as Thierry mentioned already, so in one dimension is special, that in that elementary excitations are not magnons but spinons, which can be thought of as a domain walls separating regions with locally antiferromagnetic spins. And so I flip a spin, and then by acting on such a state with my exchange Hamiltonian, I break this triplet spin one object rather into at least two independent moving objects. And so these are domain walls or spinons carrying spin half. In fact, it's not only two, it can be 4 or 6, so even number, but the 2 is gives leading contribution. So as again also Thierry showed, so already discussed, so the total energy and momentum of this spin 1 excitation is sum of energies and momenta of spinons, and given that spinon has been known, dispersion has been known for a long time, so we construct this two spinon continuum. So excitation with total spin 1 change is built out of it's essentially excitations of two spinon continuum, and the lower boundary of the continuum is given when one of the momenta say sits at 0 and another covers the allowed momentum range, and the upper boundary of the continuum is obtained when both momenta in this sum are equal to half of capital Q, and then this is upper boundary of the continuum. This boundary is not sharp, so there are excitations at high energy, but this gives a leading contribution. Okay, and so total zero momentum Q or near Q equals 0, we probe excitations in this corner, and typically neutron scattering experiment, which I'll also flash soon, probes excitations at momentum pi just because there is much more intensity. So measurements at 0 momentum and at momentum pi are complementary in each other. They probe different aspects of spin and continuum excitation. Okay, and so in this material, Zholodyev and company have done inelastic neutron scattering, and so taken from their paper. So here is some the data in which by intensity plot they show these two spin-on continuum. So H is in measuring momentum transfer along the chain, and this is frequency. And so from fits like this and taking a cuts at a given momentum as a function of frequency, and one can fit with single parameter spin-on dispersion, and in this way they determined exchange interaction along the chain to be of order 20 Kelvin. Okay. So now in ESR experiment we apply magnetic field, and so let us think what happens to this nice two spin-on continuum when I apply magnetic field. So it's very useful to think of my spin-on. So this is a sine wave dispersion for my spin-ons. When we apply magnetic field, I zoom and split into spin up and spin down, subbands if you want. And so now in the continuum, so I have to distinguish which kind of spin excitations I'm considering. So I can take spin-on with spin up and convert it into spin down or vice versa. Or I can have excitations with where spin is conserved. And so for ESR, we need the ones S plus S minus, so the one which flips spins. And then it's easy to, it's a trivial argument that at Q equals 0, it's a vertical transition, right? The two subbands are split by Zeeman energy. So which translates into this continuum picture like that. So the continuum is transformed like that at 0 momentum, minimal, the energy at which we have signal is now precisely Zeeman energy. Okay? And so if we zoom on that into this region, so the two spin-on continuum at small q has this corner shape. Okay? But so if we still have ideal spin chain, we do ESR measurement. The only point we at exactly q equals 0, we only get a single frequency response. That's all. Okay? And so from doing such experiment on ideal chain, we won't be able to learn anything except that there is a Zeeman splitting. Okay? But now we add Zoloshinsky-Maria interaction into the game. So let me for a moment apply magnetic field along the direction of vector d, which, as I said, in this material is a unique direction in a crystal. Okay, so H and D are along the same axis. Then it's a very simple exercise to show that I can do on a lattice level without doing any low energy approximation. I can transform to co-moving frame, so rotate spins into this spiral basis, where SZ is preserved, but X and Y changed into so that S plus, at every next site, I add the phase which is D over J. This is exact transformation which maps this Heisenberg plus Zoloshinsky-Maria interaction Hamiltonian into Heisenberg with weak, so second order in D XXZ anisotropy. Okay, so if you allow me for a second, forget about this d squared effect, which is I'll consider small, then by such gauge transformation, I transform Heisenberg model with Dzheloshinsky-Maria into ideal Heisenberg model. But we have to remember that what we've done is essentially momentum boost. And so if you now ask to which momentum in the transformed basis q equals 0 in the original space corresponds to, it's momentum equal by d over j, exactly. All momenta are boosted by the ratio of Dzheloshinsky-Maria to j. And so if in magnetic field my continuum is given by dashed line, when I boost it, I will effectively probe excitations at two different energies. So I'm probing my corner. I'm cutting it now not at q equals 0, but at momentum, which is ratio of Dzheloshinsky-Maria to exchange interaction. Okay. And so I have two frequencies then. I will get response at these two edges and some signal in between, depending on details of the continuum. Okay. So, so this argument is based on d and h being aligned along the same axis, but I can now extend it to arbitrary orientation for this, and it's also a very good point to describe kind of key technical steps without going into too much details, is that at low energies, spin half chain, as Thierry also already described, is equivalent to a system of actually Dirac fermions. So at low energies, I linearize around Fermi points, right and left, and these are simple Dirac fermions, and out of excitations at plus and minus kf, I can construct several important quantities. The most important for us is something m, r, and l, which are called just spin currents, but this is really uniform magnetization coming from these two regions of right and left movers. And if I allow to consider excitations with large momentum, then I can take one fermion with from right point and transfer it to left, and vice versa. And this construction will give me staggered magnetization, which is Niel vector, which is what has most of the magnetism in higher dimensions. And also in the same way, I can construct something which looks like a charge density wave in spin language. It's called staggered dimerization. Okay? And then, in order to make sure we are talking about spin chain and not about quantum wire, all we have to do is to make certain that in all these constructions, we then strip off charge fluctuations by hand, bosonization and spin current algebra approach are technical tools which allow us to do it essentially exactly. And so, but point of this exercise is to then focus on low energies and ask what Dzheloshinsky-Maria interaction corresponds to in terms of these low energy excitations. Well, one can figure out answer just by using symmetry properties. So on the lattice level, it's d dot s cross s. So it's odd under inversion. So I have to have a term in the Hamiltonian which is momentum independent, lives at q equals 0, and which will change sign when I flip right and left, the inversion. So the only combination I can do in magnetic sector is a difference of right and left moving spin currents. So if I, under inversion, this changes into minus itself. Magnetic field couples to the sum of right and left moving spin current which is magnetization density. Okay, and we can figure out the coefficient, and so there are higher order terms to which I'll get to, but this is a leading zero, so the effect of Dzheloshinsky-Maria interaction at low energies. And it's important here that this Dzheloshinsky-Maria interaction is uniform. It's constant from one bond to another. Otherwise, this argument wouldn't work. But once we have that, then we see that the unperturbed Hamiltonian describing ideal Heisenberg chain in terms of these currents MR and ML is actually a sum of squares. And so it has extended symmetry where I can rotate right and left currents coming, which describe spin excitations living at this point and spin excitations living at that point in momentum space. So the low energy Hamiltonian has extended symmetry. I can independently rotate right and left currents. So if I use this, yes, sorry, the question. Yeah.
So what is what is superscript D?
Okay, so vector D, Dzielaszynski-Maria vector, points along direction D, which is some direction in spin space, right?
This term present even the zero field?
Yes, it is, yes.
How about time reversal? It's linear with n, so how does it? Is it okay?
It is just like, it is okay. Well, yes, it is okay. A sec. So, so under time review. So right. So yes. Right. Yes. Yes. So it's a question, right? Discrete. Yes. Yes. So it's allowed. Yes. Right.
Right. The minus sign there.
Yes. Okay. So. Okay. So I'm getting there. So once we take this, so D is along axis D, H is along say Z, and so then we simply say that right moving current feels total, experiences total field, which is D plus H. Left moving current, because of this minus sign, is H minus D, okay? And so these are these two frequencies where we just have to add H and D as vectors. And then in general, we expect two different frequencies, unless H and D are orthogonal to each other, in which case it doesn't matter where it's a sum or difference, diagonal, the magnitude of the signal is the same. And so this simple H plus D vector in vector sense explains all of this data. Okay, so the splitting is relative to the Dzielaszynski-Maria direction, which is here. And if you rotate, if your magnetic field is in AB plane, you have splitting. If it's an AC plane vector, these two are orthogonal vectors, there is no splitting. And this provides for direct determination of Dzielaszynski-Maria constant, which is 0.3 kelvins, without any additional assumptions. Okay? And the very interesting and very complicated question is that of line shape, and it's still not fully solved problem. But so Jan Affleck with collaborators and Leonid Glazman as well actually have made big progress in that. But so the fact that there are two frequencies is certain. Specific line shapes is a subject of precise calculation. And then let me get to this point. So I promised to also show that interchain interaction, which in this language is described into interaction of Niel vectors on different chains, still doesn't spoil this interesting physics, exactly because of the fact that in two neighboring chains, DM vector are pointing oppositely. And so semi-classically, spins in one chains rotating, say, counterclockwise, and in the other case, they're rotating clockwise. So if you take the scalar product and average over the distance, it's gets zero. So this is a simple but argument which can be made very rigorous using our normalization group calculation, is that this special geometry leads to effective cancellation of interaction between X and Y components of chains, but the Z component is not affected. And so what happens is you promote two-dimensional magnetic order along the Dzielaszynski-Maria axis, and in the presence of magnetic field, this order is incommensurate with the lattice, and the closest analogy of it, so it's something called incommensurate collinear spin density wave state. and its closest cousin is a charge density wave. And the only excitation, and I'm closing here. So the only, if you have spin density wave, the order parameter is simply density, spin density. And this order parameter preserves U1 invariance with respect to direction of magnetic field, applied magnetic field. It is along the direction of magnetic field. Because it preserves this invariance, there are no Goldstone modes associated with, there is no symmetry breaking, so there are no usual spin waves. But what you can do, you can, similar to charge density wave, you can slide all this lattice, which is incommensurate with the lattice, and this gives you the low energy excitation, which is phase-on, the phase of spin density wave. And so here we have system where Dzelashinsky-Marie interaction, which is staggered between different chains, provides for nice, interesting measurable properties at finite energies and temperatures. And at low energy, it leads to magnetic state, which is ordered but doesn't support usual spin wave excitations. Thank you.